Well, good evening, everyone. Welcome to Mars Madness 2021. I'm your host, Robert Black, the planetarium director and astronomy teacher at North Medford High School. It's a really big night tonight. I'm really excited about our two world-renowned JPL NASA Mars researchers, Ashwin Vasavada and Matt Heverly. Before I introduce them, and their resumes could go on for hours and minutes, I'd like to just make a couple of thank yous. First of all, to our sponsors, of course, North Medford High School, where I am, and of course, the Southern Oregon Skywatchers, local astronomy group, and ScienceWorks, Hands-On Museum. They've all helped us put this together. And also Colin White, he's gonna man the question and answers for us tonight. Thank you, Colin. He's a solar system ambassador with the JPL. He's a great contributor to the science community here in Southern Oregon. Thank you, Colin. The chat has been turned off, I'm almost certain, for all of you attendees. But if you would pose your questions in the Q&A, Colin will get to those. The format tonight, we're going to start with Ashwin, and then he's going to transition into Matt's talk. And when we first put this together, they talked about kind of the past and the research of Mars, the present, and then we'll move on to the future. So it's kind of a nice, kind of a blending of what we have. But starting out tonight, we have Ashwin Vasavada, and he's got an incredible resume. My students and I have been studying him. He's been working at the Jet Propulsion Laboratory since 2003. He's been working to set up Curiosity, and he leads an international team to study the data and conclude information from the Gale crater there on Mars. So thank you so much for being here tonight. He's got a Bachelor's of Science from UCLA in geophysics and space physics, and then a PhD from Caltech. Yeah, and then of course Matt Heverly, one of the greatest robotic engineers there is. He of course got his bachelor's at Cal Poly San Luis Obispo. Wow, it's a mouthful. And then of course got his master's at Boston University. He's been working, driving rovers on Mars since the beginning there, I think, with Opportunity, then moved on to Curiosity, and now he's in the future, the sample return. So thanks to them for being here tonight. Last thing I'm going to say before I get Ashwin to start us out is their connection. I think how we got them here tonight is both of their parents live here in Medford. So thank you to their parents if they're listening for living here. Thank you very much. So let's all give a virtual welcome to Ashwin Vasavada. Thank you, sir, for being here. And it's all yours.
Okay. Well, it's really great to be here. Thank you for the introduction. Thank you for that wonderful slideshow beforehand. And thank you for the 70 plus people that are attending. It's really great that you're excited to hear about Mars Madness, because Matt and I are really excited too. This is a wonderful time at NASA and at JPL, because we're at the 8 years into a very successful rover mission of Curiosity, and about to get a new rover on Mars in February, which Matt will talk about. And so it's a really exciting time for us, both looking backwards and looking forwards. And I have the job of telling you what Curiosity has been up to for the last 8 years, and how it sets up Perseverance to land on Mars in mid-February and take the next leg of the journey. So for those who don't follow this super closely, Curiosity and Perseverance are both car-sized rovers. They look fairly similar to each other because they have a similar design, but they have different science objectives. And this is a picture of Curiosity, an animation of Curiosity. And this is the crater that it's in, Gale Crater on Mars. I'm Ashwin Vasavada, as you heard. I'm the project scientist, which means for the past 5 years or so, I'm the second project scientist on this project. For the past 5 years or so, I'm the one that gets to work with scientists all over the world. We have 500 people around the world involved in this mission, from something like a dozen different countries, but of course, working through NASA JPL in Pasadena, California. Well, it has been 8 years, and we just passed a milestone of 3,000 sols. A sol is a Martian day, just slightly longer by about 40 minutes than an Earth day. So it's actually been almost 3,100 Earth days, but 3,000 sols. And just, when you look at the rover, it not only looks like it's in great shape, it actually is in remarkably good shape for being 8 years in. When you look a little closer, you start to see that that what used to be a very nice white painted deck is now covered with Martian dust. The rover is actually starting to become a little bit camouflaged as it drives around and gathers all this dust. And the wheels have some pretty big holes in them, a problem that Matt and his team fixed on the next rover. But Curiosity was a little surprised by the sharp rocks it encountered on Mars when it first landed. But really, there's not much else in the way to talk about major problems with the mission. 8 years in, and we're still going really strong after 3,000 sols. And, I guess one thing you may be wondering is who took these pictures? It's not in Hollywood. This is on Mars. But we actually have a big arm on the rover, and the rover actually can take selfies with its own camera on the end of the arm. And when you take enough of those, you can actually Photoshop out the arm itself and get a nice picture of the rover. We did this for fun early on in the mission, and then it just turned out to be a really useful way of kind of marking our progress at different sites that we found important. Well, one of the things I'm going to do in this talk is kind of describe why both Curiosity and Perseverance are sent to Mars in the first place. Why do we as a country and the world and as scientists find Mars interesting? Mars is, of course, the next planet out from the sun than Earth. It's about half the diameter of Earth. And right now, as you can see on this picture from the Hubble Space Telescope, it is a dry planet. There's no liquid water to speak of. Very little chance probably that there's life today on Mars, if there ever was life. Today would be not one of the best times for it to exist. It's very dry, no liquid water, but it does have just enough water in the atmosphere to form these little wispy clouds. And also up at the polar caps, there are some pretty massive ice deposits. So gives a hint that one day maybe there was some liquid water that now is just all frozen out at the poles and just a little bit of vapor in the atmosphere. In fact, what we think is that a few billion years ago, Mars may have looked something more like this. This is probably a best case scenario for what Mars may have looked like if it had water at one point, where you have an ocean filling up the northern hemisphere, filling up some of these big valleys and big weather systems going across the planet. It very well could have been this way. And that really is one of the reasons why we're so interested in studying not only Mars, but ancient Mars. Because if Mars once had all this water and is not too far, much farther from the sun than Earth, and has a lot of the same materials that Earth formed with, it's not that much of a stretch to wonder whether Mars may have had life, whether life originated on Mars just like it did on Earth. So that's one of the main reasons that NASA studies Mars, as well as some other planets in the solar system. We're interested in figuring out if there's any life beyond Earth. Well, how do we know that this idea that there was once liquid water on Mars might be correct? Well, we have had lots of satellites sent to Mars over the past few decades. And one of the first ones, almost 50 years ago, found these river channels in between some of the craters. So the very first spacecraft that we sent to Mars in 1964 found all these craters over the surface. It actually ended up looking a lot like the moon, and it was a little disappointing, frankly. But just a few years later, we sent another one around 1971, and it had a little better camera, and all of a sudden, the places in between these craters were filled with these river channels. As we got better and better cameras at Mars, we saw that there was massive floods that once scoured the surface. These channels are about a mile or tens of miles wide in some places. So these are huge floods, the kind of thing that on Earth happened at the end of the Ice Age. when there were massive floods that scoured parts of the continents. When we got even better cameras at Mars, we began to find features like what's on the right here. This is actually a river delta. So this is only about a mile across top to bottom. And when you look in really carefully at an image like this, you can begin to see that there was a river that flowed from the left towards the right. And that river even had oxbows in it, like you'd find in rivers on Earth, where the river, slowly piled up mud against its bank and began to turn. And as the river flowed downhill and encountered a flat plain, it spread the mud it was carrying in all these different directions. This is a classic river delta, like you'd find, at the end of the Mississippi River if you were to remove the ocean. So not only does this tell us that water flowed on Mars for a long time, but it tells us that there was lakes on Mars as well, because this kind of delta is what you get when a river flows into a standing body of water like a lake. So we think, we're pretty confident, in fact, that Mars was once wet. We'd like to know if it was also warm. Was the climate such that it did have these big storms that could be a lot of rainfall and could really make a Earth-like climate system? And then the real question that the Curiosity mission is centered around is, was Mars ever habitable? And if it was habitable, how long was it habitable? So Curiosity wasn't sent to look for life. Matt will tell you about his mission that he worked on, Perseverance, about that. But Curiosity is sort of a precursor to that. We're asking the question, were the conditions ever right for life to exist? So what does it mean to be a habitable planet? This is a place in California, Death Valley, which is not the first place you'd think of as being habitable, but really it's teeming with life like everywhere else on Earth. And really, for life to exist on Earth, you just need a few criteria to be met. You need liquid water. All life as we know it requires liquid water. So we'd like to find that on Mars. You need the chemical ingredients of life. You need the things that our cells are made out of: carbon and hydrogen and oxygen and phosphorus and sulfur, those sorts of things. And you need an energy source. Now, of course, the sun is a big energy source for Earth and Mars, but on Earth, microbes can use other sources of chemical energy too, like the various minerals that are in rocks underground. So we can look for that sort of thing on Mars as well. Well, then what do you do when you have this goal of studying Mars habitability? How do you actually accomplish it? Well, you build a car-sized rover and you equip it with various instruments that can look for signs of ancient water, signs of ancient chemical building blocks of life, and signs of those ancient energy sources for life using various instruments. And one of the main ways we do that is by having a big drill on the end of the arm, so we can drill into rocks that are dating from 3 billion years ago when we think all the water was there. We can drill into those rocks and look for the kinds of things that would tell us whether Mars ever was habitable. Our most fun instrument, of course, is this laser. Both Perseverance and Curiosity have a laser that can shoot up to about 15, 20 feet away. And we create a little spark on a rock with this laser, look at the detailed color information of that spark, and that color of the spark can tell us what chemicals are present in the rocks. So it's a neat way of not having to drive up to every single little rock. You can actually zap a bunch of soil and rock around the rover and actually see if you see any of these chemicals that you're interested in. Well, now we have a rover that's very capable of figuring out if Mars was ever habitable. Now we got to send it somewhere that would give us a good chance of discovering such an ancient habitable place. And we found a place that we really love, which is called Gale Crater. And Gale Crater is a crater that's about 100 miles across. So it's a big hole in the ground that formed a long time ago when an asteroid hit Mars. But what's different from most other craters on Mars is it has a mountain in it. And this mountain, it didn't get there by itself. It's mysterious how it got there, but one of the ways that it could have gotten there, we thought, before we got there and discovered it ourselves, was that maybe rivers brought in sediment into this crater by, carving out the crater rim, a river flowing down and depositing silt and mud in the crater itself. It could have been that. It also could have been a bunch of wind that brought in this material. So we weren't quite 100% sure, but we took the chance and sent Curiosity here because this crater just had such a beautiful mountain to explore that really we thought had a good chance of being present because of all that water in the past. So we landed now about 8 years ago. This is that crater now from the top, and this is the mountain. And for the past 8 years, we've been driving. We landed on the plains next to the mountain. We spent about a year driving towards the mountain. And then for the last 7 years, I guess, we've been driving more slowly and methodically up foot by foot of the mountain, studying it in great detail, trying to understand its history and how much water was there and whether Mars ever really was a habitable place. And so over 3,000 sols, we've driven 15 miles and climbed about 1,350 feet in elevation. So it's been a very fun and productive road trip for us, and we've discovered a lot. One of the first things we found, right after landing, in fact, was that some of the rocks around the rover were falling apart. And as they were falling apart, the pebbles that were in the rock were falling out, and we could look at them and they were all rounded. And to the geologist, that means something very special. That means that these rocks were rounded because they were hitting each other and tumbling over each other as water was carrying them down an ancient stream bed. This is something that's very common on Earth. We have all, walked across a riverbed and felt those rounded pebbles beneath our feet. But this is the first time we'd ever seen such a thing on Mars with our own rover eyes to confirm the fact that Mars really did have water flowing across its surface. So just within a few months after landing, we had this great discovery that we were really onto something in Gale Crater in terms of finding evidence for ancient water. As we drove further towards the center of the crater, we came across landforms like this. Now, these are sandstones that are all in kind of a slab form and all tilted towards the center of the crater. And this is exactly what you'd expect if you were following a river and that river encountered a lake, and all of a sudden all the sand that river was carrying as it was flowing fast downhill all of a sudden fell out of the river because the river now was going into a lake and slowing down. So the sand falls out and it forms these slabs or these layers of sand that eventually turn into sandstone and leave formations behind like this. So this is a river delta that we found as we were driving towards the middle of Gale Crater. So now we have the upstream part of a river where the pebbles are. We have the middle part of a river where it enters a lake. Now, if we were to drive further, we should find all the fine silt that the river carried into the lake that then deposited onto the lake floor as muck and mud. And so that was an exciting part of the mission where we got this far, and now we would drive further and actually hope to find evidence of those lakes themselves. And of course, I'm talking about evidence of lakes trapped in the rock that we look at 3 billion years later. And this is what it looks like. So these are the kinds of rocks that we saw when we got to the center of more to the center of the crater and finally started climbing the mountain. And the rocks at the base of the mountain were formed layer by layer. These are just millimeter thick layers, but hundreds and hundreds and thousands of them as we drove higher and higher up the mountain. And each one of these layers can be traced for a long time, and it's made out of very fine-grained silt kinds of sediment that then formed into rock. And so this is just what you'd find if you were to dig underneath a lake on Earth, dig into the rock, below a lake on Earth, where these layers of mud that were once carried in as silt from a river would fall on the lake floor, and over the eons, turn into rock. So we've now, at this point in the mission, we'd convinced ourselves that we really had found a river and lake system in Gale Crater, and we went to a place where we could drill into that mud and see, put the material that we drill into some laboratories in the rover and figure out if we could see those other criteria that would tell us that this was a habitable place. And so we drilled into that lake floor mud and analyzed it with some pretty sophisticated chemical instruments. And we found that the water that formed this lake was actually fresh. It actually was not too acidic. It was not too salty. It formed and left the kinds of minerals behind that would form really similar to what would happen in a freshwater lake on Earth. So this was also very good news for the idea that this was a place that life, if it ever existed, would find pretty habitable, pretty hospitable. To make things even more exciting, those experiments we did on the samples we drilled from this rock also found evidence of carbon-based molecules. So, we talked about wanting to find those building blocks of life. We found carbon, we found hydrogen, we found oxygen and sulfur and phosphorus, but we even found molecules where those chemical elements had begun to form into organic molecules or hydrocarbons, a little bit more complex molecules. Not quite the complexity of the, things you'd find in our cells, amino acids and things like that, but a start. And, it's pretty intriguing that the machinery of life maybe had begun to form, or maybe we're seeing the very degraded products after 3 billion years of actual life. Curiosity isn't equipped to be able to answer that question. That's what Perseverance is for. But the fact is, we found this really intriguing evidence. This is what it might have looked like. So even if Mars never was super warm and wet, and maybe if it never had those very big weather systems, even an environment like this that you find in the Andes in Chile on Earth would be enough, for life to flourish. These are lakes that are high up in the mountains where it's very cold and very dry, but it's still enough water for these lakes to stick around year-round and host life. Well, after 8 years, we've climbed a lot of the mountain, and we continue to do the same kinds of experiments we did at that very first lake that we found. And we've drilled now 29 more holes into the rocks of Mars, each time asking those same questions. Are we seeing evidence for water? Are we seeing evidence for the building blocks of life? And are we seeing those energy sources that life needs? We found an incredible variety of environments on ancient Mars. Each one of these drill holes is a slightly different color. So it tells us that the conditions weren't all the same. Sometimes the rusty color of Mars has penetrated into the rock, and what you drill is actually just as orange as the surface. Other times, you drill into an orange rock that's the color of Mars, and the material inside is gray. And that was actually even more exciting for us, because that means that all the oxidation, the rusting of Mars that happened, did penetrate very deeply in this area. And that oxidation, that rusting of Mars, could also destroy evidence of ancient life that once may have been there. So if we're going to go look for signs of life with Perseverance, the fact that Curiosity found places where that process that could destroy such evidence didn't actually happen, or didn't actually happen that deeply even, that's a very good sign for actually discovering life one day on Mars. Well, the lakes persisted for a lot of the mission. We found evidence at almost every level of the mountain that we've been at for these lakes. But in rare instances, as we climbed up the mountain, we did find that the lakes disappeared, that they dried up. And this is just a really neat rock that we found, where there's actually, there was a lake at one point that left a layer of mud behind. And then at some point, the lake receded, exposing that mud on the shoreline. And the mud actually, under the heat of the sun on Mars, it began to crack. And what you see here are kind of the imprints of those mud cracks that are left behind in this rock. So I just think it's I thought this was always pretty fascinating because these mud cracks probably formed just in a few days on Mars. So it's we're seeing something that happened just in an instant of time 3 billion years ago on Mars, which just seems fascinating to me. Well, after 8 years of climbing the mountain and drilling 29 holes and looking at all this different evidence, we now know that Mars had liquid water, not just for enough time to form one lake, but enough time to form lakes over hundreds of meters of vertical elevation on this mountain. The lakes just rose and rose and rose as more and more mud came into the crater through the rivers. So liquid water was there on Mars for millions of years. And in various holes that we've drilled into these lake sediments, we found more and more evidence of organic molecules too, sometimes more complex molecules than we first found, sometimes less complex, sometimes more degraded, sometimes less degraded. So there's just a lot of variety in what we're finding, but it all points to the same conclusion that Mars once was a place that had all the conditions necessary to support life. Now, this is just, honestly, I just threw this in here because I love the picture. It's just a gorgeous place, one of the places we drove through. This is the lake floor sediment that we drove across. And then these are some fantastic buttes from sandstones that formed that once used to cover this whole area. So you can imagine this layer of sandstone used to just be across this whole area, and this was filled in. But as billions of years have gone by and wind has slowly carved all the rock away, all you're left with are these towering buttes, just like you're driving through Arizona or Utah. And then this is just another beautiful picture that we took not too long ago from now, 1,300 feet of elevation up on the mountain. We can look back on the crater plains where we landed. And one of the reasons I really love this picture is because you kind of look out here and you can almost convince yourself this must have been taken out in the Mojave Desert on Earth somewhere because it just looks so Earth-like. But then you look over here and there's this giant hole in the ground that's from an ancient impact crater, one of those craters that formed on Mars, billions of years ago that are very rare to find on Earth. So, you have this very Earth-like scene, but then this reminder over here that you really are on Mars. So Mars was once wet, and was it also warm? Quite likely, we think so. From all the evidence that we have, from the fact that lakes persisted for millions of years, they filled this crater, rivers carried pebbles and sand and sediment for all that time, and there must have been some big weather systems, good amount of rainfall on ancient Mars, and all that takes a relatively warm climate to happen. And was it habitable? It was, and for how long? We think about tens of millions of years, or maybe even more. So the amount of rock that we've looked at so far in that 1,300 feet on Mount Sharp tells us that there is probably at least tens of millions of years of history recorded there. But we still got a lot of climbing left to do, and maybe the lakes will continue higher and higher and higher. And so maybe there'll be even much more time recorded in these rocks of Mount Sharp as well. So that brings us to the next step in NASA's exploration of Mars. So Curiosity was designed, well, I should just step back and say Curiosity and Perseverance and the rovers before it, Spirit and Opportunity, are all part of a strategy of exploring Mars. The first thing that NASA wanted to do with Spirit and Opportunity, which were rovers that landed in 2003 and 2004, was to figure out if Mars had liquid water. And those rovers answered that question. Yes, Mars had liquid water. Then that was followed up with Curiosity to ask, okay, Mars had liquid water, but was it a habitable place? Was the liquid water in the right form, not too salty, not too acidic? Were those chemical building blocks of life there? Were there organic molecules? Were there energy sources for life? And so Curiosity was sent to ask that question, and it answered it with a big yes. Curiosity found that Mars was habitable. It had all the conditions necessary to support life. So then you go to the rover that's landing next month, which is tasked with asking the next big question. And it's equipped to actually answer that question, which is, did life ever exist on Mars? If Mars was habitable, did life ever take hold? And so you have this wonderful rover, Perseverance, that's actually seeking signs of life. And what does that mean? It's looking for patterns in the rock textures, in chemical elements that it finds, other organic molecules that it might find that are unique to life. It'll be able to tell when it finds a texture or an organic molecule of a certain kind that it can rule out other ways that might have been caused other than life, to be able to prove in a sense that what it's finding is actually due to the presence of life 3 billion years ago in the evidence that's trapped in the rocks. And one example of that is what the image that's shown on the right here. These are what are called stromatolites. These are rock textures that are now turned into rock, but used to be what are called microbial mats, or places where microbes used to live on the surface of these rocks. And the microbes themselves caused the minerals to precipitate in these wavy patterns. So when you see a texture like this on Earth, it's a definitive sign that life was present. And you can distinguish that from just any old other rock. And so that's the kind of thing, both from a chemical and textural point of view, that Perseverance will do. And so now, that's all I'm going to say about Perseverance, because Matt's going to tell you the rest. But that's where Curiosity has left the state of Mars exploration and has teed it up perfectly for Perseverance to take over. So Matt, take it away.
Awesome. Thanks, Ashwin. Let's see. I'll share my screen here. Let's see. I think I need you to stop sharing, Ashwin, and then I'll take it from you. There we go. Thank you. All right. Can you see my screen there? I've got a thumbs up. Awesome. So thanks, Ashwin. I totally appreciate you giving the great background, and it's so fun to see all the things that the Curiosity mission has done. I was able to work with Ashwin for several years on that mission, and it is just amazing to see that rover still going and making awesome discoveries. So I'm going to today, as Ashwin said, talk to you a little bit about the follow-on mission to that, the Perseverance rover. I'll start out with a quick little video here. It's always so fun to see the effort that it took to put these missions together, and all the work of the hard work of the people that it took to build these things. And what comes out of the other side of all that effort is this amazing rover known as Perseverance. And one of the first things you can notice about this rover, as Ashwin pointed out, is it looks really, really similar to Curiosity. And that's intentional. What we've done with our arc of exploration is we've tried to build upon the successes of our past. And just like scientifically, where our Spirit and Opportunity rovers were looking for water, and Curiosity was looking for habitability, and we're building upon that scientifically. We're also building upon our engineering experience. So when you look at this, it's a very similar design, right? We have our 6 wheels, we have a robotic arm, we have a sensing mast, it's about the same size chassis. We have the same way that we're delivering the rover to Mars, because all those things worked so well for the Curiosity rover. So we're trying to build on that success, but now we're trying to answer different questions. And as Ashwin said, you know, we're building on that. And while we've always kind of had this geology objective A, the Perseverance rover is now looking at an objective of understanding astrobiology. Was life ever there on Mars? Is life unique to Earth? And in addition to those questions, we're doing 2 other major things where we're caching samples, meaning we're collecting samples ultimately for return to Earth. And then the last one is we're making another step forward in preparing for humans to explore Mars. So when we look at our rovers, you know, they look very similar, but our 7 scientific instruments are different in that they're enabling this new level of science. And like the Curiosity rover, we take a lot of pictures, right? There are 23 cameras on our rover. And just like you, if you were going to go to the Grand Canyon and look around, you'd probably take a lot of pictures. And that might be one of the things that you look at to understand, you know, what is the texture of these rocks? How are they placed? So that we can piece together that story. And we're not going to do anything differently there. We've got our mast cams, which are our zoomable, panoramic color stereo cameras. They're incrementally improved beyond a little bit better than our Curiosity rover because they've got these zoom and focus mechanisms, but they're still fundamentally just really great cameras. We have a laser on this rover too. I always love it when we get to tell people that our rovers have laser beams that we get to shoot at rocks on Mars. We've got Meta, which is a weather station. You can follow on Twitter. There's @MarsWeather, so you can know what the weather's like on Mars if you're at all interested. And then we've got a new instrument called RIMFAX, which is a ground penetrating radar that will allow us to understand the subsurface of Mars, to look for some of that structure, to piece together how things were formed. And when we look at kind of our astrobiology objectives, it's really these 2 instruments at the end of the robotic arm, are Sherlock and Watson. And as Ashwin said, these are mapping spectrometers so we can look at structure. So we can not only understand what is the chemical makeup of a rock, but we can understand how is it structured in that rock to look for evidence that maybe that was biomediated or it came from life. And we not only try and do these scientific objectives, but oftentimes we have experiments on our rover. And our MOXIE instrument is an experiment. And that's to fulfill that last objective of preparing humans to return to Mars or to go to Mars. And we'll be able to produce oxygen, both for astronauts to be able to breathe if we send people there, and to maybe produce rocket fuel in case we want to launch rockets off of the surface of Mars. We can use that CO2 and separate it and get oxygen that we can use to be able to use the resources that are there instead of having to take all of those things with us. But I think one of our most exciting experiments is the Ingenuity helicopter. So this is an engineering demonstration that we're trying to do. It really doesn't have any scientific objectives, but what we're trying to do is build the first powered flight vehicle on the surface of another planet. And this is a drone helicopter, just like you would fly a drone helicopter here on Earth. But one of the problems is the atmosphere of Mars is about 100 times less dense than the atmosphere on Earth. So where, you know, my son has a drone helicopter and it's got these little tiny blades that it can fly around. In order to fly in the Martian atmosphere, we have these gigantic 1.5 meter diameter blades that are counter-rotating blades that lift this very small payload that's just a small computer, a few solar arrays to be able to power a battery and a camera. And it can be able to fly around on the surface of Mars. And as I said, this is really just a technology demonstration. So we're trying to understand if this is a viable way for us to explore Mars. And if so, then our future missions, instead of seeing rovers, you may see schools of drone helicopters that we send to Mars to be able to do that exploration. And all of this equipment was designed and built at the Jet Propulsion Laboratory. And we started the design of the Perseverance rover shortly after Curiosity was successful on the surface of Mars. We knew that that had worked, and we knew that we wanted to build upon that success. So over those 8 years, as Ashwin has been exploring the surface, another team of engineers have been designing and building this vehicle. And it's not just the design and build of this, it's really the testing of it as well. You know, Mars is a long ways away and we only get one chance. We don't get to send somebody to Mars to change out the wheels if they fall apart, or we don't get to send them to Mars to reboot the computer. So we got to make sure that the rover can handle all those things on its own. So we do a ton of testing with these vehicles here on Earth. This is one of my favorite pictures as somebody that is a mobility engineer. This is the rover's first drive for the flight vehicle as it's in our facility where we assemble it to make sure that the actuators are working, that it can drive over obstacles, and that everything's going to work as we expect when we get to Mars. But it's not only the rover that we build at JPL. We build the entire spacecraft that it takes to get to Mars and then safely land on Mars. And as we designed and built this in January of 2020, we shipped all of this over to Florida to be able to do the final assembly before we put it on top of the spacecraft to launch put it on top of the rocket to launch it off to Mars. And Mars only comes around every 2 years. If you think about Earth and Mars are both orbiting the sun, you know, you don't want to launch your rocket when they're on opposite sides of the sun. That's a really long distance. So we want to wait till they line up, and that's really only every 2 years. So if we miss that window of opportunity, we won't be able to launch the rover for another 2 years. So you can imagine the pressure as we're putting this whole thing together. This image is one of the last pictures that was taken where you can see the rover right before we put that heat shield up onto the bottom of the rover. And this was in the early February timeframe of 2020. And in March, our rover got its name. All of our rovers are named by elementary or middle school students. This is Alex Mather. He's a 7th grader from Virginia. And he wrote an essay that was selected that named our rover. And he named it Perseverance. And none of us really appreciated how apt that name was. You can imagine when this came out, this was March 5th when we got our new name. And then just like all of you, the world changed for all of us. And we had this launch window where we only had about 2 weeks when we could launch this rover off to Mars. And it was in the middle of July. And if we missed that window, we'd have to wait another 2 years. And the team down in Florida at Kennedy Space Center, finishing the final assembly of this, integrating it to the rocket, preparing the rocket, they just worked tirelessly through this new pandemic that hit all of us. And everybody kind of remembered this name of this rover, and they persevered and got it to the launch pad. And on July 30th, we successfully were able to launch off and start our journey. And it was pretty amazing to be able to achieve that milestone. And our rover right now it's in its journey. I pulled this morning. We've gone an amazing 414 million kilometers. That's how far the rover has traveled so far. We've got a mere 55 million kilometers left. We're 88% of the way there. And on February 18th at 12:30 Pacific time, we will attempt our landing on Mars. And everybody should mark your calendars. This is a thing that we all get to watch together. There's no, we don't get to watch it first and then tell you if it worked or not. We're all gonna watch it at the same time. And it's a really hard thing to land a spacecraft on Mars. First of all, we have to get there. This is the spacecraft in its cruise configuration. You can see the solar panels on the back there to collect the power as we go to Mars. And there's our little thrusters here. So as we go to Mars, if we need to turn left a little bit, we can hit those thrusters or turn right or speed up or slow down. That will let us get to exactly where we need to be on Mars to allow us to land at the target location where we want to land. And right before we get to the atmosphere, we jettison this cruise stage and it goes away, and it's just our entry vehicle that goes, and then it hits the top of the atmosphere. And as I said before, the Martian atmosphere is 100 times less dense than the Earth's atmosphere, but it is still dense enough that it will slow our spacecraft down significantly. And as it's moving at this super high velocity and it hits this atmosphere and slows down, it generates a tremendous amount of heat from the friction of it interacting with that atmosphere. And the heat shield protects our spacecraft as it slows down, and it will speed across the the atmosphere, and it will steer itself. So it will turn a little bit left and it will turn a little bit right in order to kind of correct any trajectory changes that it needs to add in order to hit its target when it gets to Mars. And it'll slow us down a bit, but we need to slow down even further to have a safe landing. So the next thing we do is we deploy a parachute. And this parachute deploys at about Mach 1.7. And you can imagine as this inflates with this car-sized rover going hundreds of miles an hour, it's gigantic loads that get put into the system. And we have amazing engineers at JPL who design these parachutes and all these structures to make sure that the rover can stay safe. And that'll slow us down a little bit more, but it doesn't slow us down enough to land safely. You can imagine when you see people parachuting here on Earth, you know, they hit the ground and they kind of run along, but it's a nice soft landing. But when your atmosphere is 100 times less dense, you have to do something differently. And we use a jetpack on the back of our giant car-sized rover. And I distinctly remember the first time that I saw this concept, it just seemed so crazy to me. We're really putting a jetpack on our 2,000-pound rover and flying it around. But yes, this will allow us to navigate to where we want to go more precisely, and it will slow us down, and we'll get to about 10 meters above the surface, and we'll come to a stop, and then we'll lower the rover down on this bridle. Because the rover is so heavy, we don't want these retro rockets to get too close to the surface. It'll blow up a whole bunch of dust that might damage the vehicle, might damage, get in the way of those rockets. So we keep those rockets away from the surface and we lower the rover down. You can see that the wheels are kind of tucked up in order to fit in that aeroshell. So we'll deploy those wheels, and then the descent stage will lower slowly a little bit more until the wheels touch down on the surface. And we sense that there's no longer tension on those bridles, and then we will cut those bridles, and then that jetpack will fly away and it will crash somewhere, hopefully very far away from the rover on Mars. And hopefully Perseverance will land safely, and we'll all get to watch that together on February 18th. And one of the most amazing things to me about this is that the rover has to do this all on its own. That entire sequence is autonomous. And the reason it has to do that is because Mars is a really long ways away. So currently it's about 160 million kilometers. It takes the speed of light about 9 minutes to go from Earth to Mars one way. So you can imagine if I'm flying my son's remote control drone and I say, hey, go up, then I'll send that command, and then 9 minutes later, that drone would start to lift up. And then when I wanted to move back down, you know, I'd hit down, and then 9 minutes later, it would go down. And we can't control our robots that way. We can't do it for either landing safely or for driving around on Mars. So once the rover's safely on the surface, the way that we have to communicate with it is we talk to it roughly twice a day. So once in the morning, we will send it a list of commands of what we want it to do on Mars. And you can imagine this as just your to-do list for the day. And we send it basically an email that has its to-do list for the day. And it might say, you know, drive forward 1 meter, take a picture over to the left, turn right 10 degrees, drive forward another meter, deploy your robotic arm, make this measurement, et cetera, et cetera, et cetera. And the rover will receive all these commands at roughly 10 o'clock on Mars. And then it will wake up and it will look at its list and it'll say, okay, the first thing you wanted me to do was, you know, drive forward 1 meter. So it will drive forward 1 meter. And once it executes that successfully, then it will move on to the next thing. All right, take my picture over to my left. So it'll turn its mast and take the picture, and it will continue down this list of activities that we give it. And we can give it commands at various levels of autonomy. So we can give it very low levels, you know, spin this motor 3 times. Or we can give it something very high level, drive from where you are over to this rock and just get there safely. We don't even know what's in between you and this rock, but you need to get there safely. So the rover can drive autonomously. It will drive, it will image to see if it's safe in front of it. And if not, it'll turn right and go around that rock and drive forward and then continue to get to its destination. And it's using very similar algorithms to what your phone might use if you were using Google Maps to drive around. And you know, you're driving, and if there's an accident on the freeway, Google Maps might tell you, hey, get off the freeway and take the surface street. And it's the same algorithm, right? Go down this road, there's a rock in front of you, get off the road and go around and find a safer route. So then once the rover has achieved all of its objectives for the day, it will send that information back home. And it doesn't have enough power to be able to transmit it all the way directly to Earth. So we talk to Earth through our orbiters. We have a lot of orbiters around Mars, and the ones that we communicate with are in what we call a sun synchronous orbit. So they go over the same spot on Mars at the same time of day every day. So at roughly 5 p.m. on Mars, this orbiter comes over, and the rover will transmit all the information to that orbiter. Hey, remember that picture you wanted me to take? Here it is. Here's that data from the motor when you wanted me to drive forward. Here's all these things that you wanted me to collect. I'm going to send it to the orbiter. And then the orbiter sends it back to Earth, and then the rover goes to sleep at night. It's really cold at night on Mars, so the rover saves its energy for exploring the next day, and it doesn't do a whole lot overnight. But while the rover's sleeping on Mars, the humans on Earth are preparing to understand what it might want to do the next day. So the scientists and the engineers will get those pictures and that telemetry and all that information. Scientists like Ashwin will say, hey, let's go over to that rock over there. It looks like a really cool mudstone. And they'll tell the engineers, all right, why don't you drive the rover over to get to that rock? And while the rover is sleeping at night, we'll prepare those commands so that we can send it up tomorrow morning at 10 o'clock a.m. on Mars. And the problem is that those times are the times on Mars, not the times on Earth. And the Mars day is slightly longer than the Earth day. It's about 40 minutes longer than the Earth day. So while 5 p.m. on Mars might be 8 a.m. on Earth on Monday, so we'll come into work at 8 a.m. on Earth and get that information and plan during our workday. On Tuesday, 5 p.m. on Mars is actually 8:40 a.m. on Earth. And on Wednesday, it's 9:20. So every day the operations team would come into work 40 minutes later, and we would all show up to work at 5 p.m. on Mars, no matter what time it is on Earth. So for a lot of us, we would work on Mars time when we worked on these missions. Now, we don't work on Mars time for the entire duration of the mission. We only do it during the first portions. But it is this very interesting dynamic where the people working on the mission, your whole sense is really tied to this other planet. That's where your rover is. That's where your clock is, where you're deciding when you need to wake up and go to bed. And it's a very, very interesting experience. And where we're trying to go with our Perseverance rover on Mars is this place called Jezero Crater. And this is an ancient impact crater that you can see turned into a lake. And you can, the map here, purple is low elevation and green is higher elevations. And you can see this lake inflow channel over here where there was a river that flowed into this lake. And then you can see where the water flowed out of the lake over here. And as Ashwin said, the places we want to go are places that had this flowing water. And we also want to look for places where evidence of past life could have been preserved. So as Ashwin said, these deltas are amazing places. So the place where we're going to try and land is at this delta. And this is, as the river flows in and it hits the standing body of water and deposits all these things and then buries it and preserves it. This is a prime scientific area for us to go explore. And when we explore, we're going to want to explore all over this delta, right? The base, we're going to want to get up on the delta. We're going to want to get up on the crater rim, just like Ashwin had said, as he's exploring all these different places in Gale Crater. And as we go, we will use all of those instruments to kind of understand the context of the geology. We will use our instruments on our arm to understand what rocks might have the greatest chance of preserving past life. But we don't think that we can actually take all of the instruments necessary to reach that burden of proof on Mars to say, this was definitely life. We believe in order to really do that, we're going to have to bring those rocks back to Earth. And the way that we're going to do that is we're going to collect samples with our rover. So this rover, Perseverance, has a drill a lot like the Curiosity rover, but the drills are a little bit different. Where Curiosity was a powdering drill, where it would drill down and collect fine powder of that rock, as Ashwin showed, adjacent to those holes, and put it into its instruments on board the rover, we will drill down and try and collect a sample. So this will be about the size of a piece of chalk, and it's a hollow drill bit that goes down and breaks off this core, and then it will ingest the core into the body of the rover and put it in a little tube, looks like a test tube, it's a sample tube, and then we will hold on to it. And then we'll go explore another place. So as I said, we might look at the base of the delta, and we might climb up the delta and collect another couple of rocks there, and then climb up onto the crater rim and collect another couple of rocks there. And then at some point in our mission, we will decide, okay, this is the place, and we will eject all of those samples and we will put them down on the surface of Mars. Because the Perseverance rover only has the ability to collect these samples. It doesn't have the ability to actually get them back to Earth. So in our arc of Mars exploration, this is where the Perseverance mission ends. And the next mission, which I'm working on right now, the Mars Sample Return mission, comes in. So with this project, the Sample Retrieval Lander, we will land on Mars with a lander. And on the top of this lander will be a rover. You can see it kind of upside down here with its wheels sticking up in the air. And we'll deploy this rover down onto the ground. And then this rover will drive over and it will attempt to pick up those samples that were cached in a single location on the surface of Mars. And one of the things that's interesting about this mission is it's so ambitious and so big and so expensive. We don't actually think that we can achieve it all on our own as NASA. So very similar to the International Space Station, that is an effort not only by NASA, but by all sorts of international partners. So this rover is actually built by the European Space Agency, and the return of these samples will be an international collaboration. So once this rover picks up these samples and puts them into a storage rack on the front of the rover, it will return back to the lander, and a robotic arm on the lander will go extract those samples from its storage rack, and it will go place them in the surface of a rocket that we will take with us that will be inside the belly of that lander. Now, we'll only be able to bring back about 30 samples, and we'll have to choose, the Perseverance rover has 43 tubes on it, and we'll have to decide which of those 43 samples do we want to bring back. We'll have to select the 30. We'll put it into the top of this rocket and launch it off of the surface of Mars. It'll be the first time we've ever launched a rocket off the surface of another planet. But this is a relatively small rocket. It's only a couple of meters long, and it's not going to be able to get all the way back to Earth. So once this rocket gets into orbit around Mars, it will eject this box full of rocks, which is our, we call it the orbiting sample. And it is a container about the size of a basketball that has those 30 tubes. And the rocket will descend and then burn up back into the atmosphere of Mars. But this orbiting sample will be in orbit around Mars. And we will have another spacecraft, the Earth Return Orbiter, that will go rendezvous with this basketball-sized box full of rocks. And it will ingest this orbiting sample into that spacecraft. And then this spacecraft will use electric propulsion. You can see it has these giant solar arrays, so it can generate a lot of electricity. And it will turn and it will start its long journey back to Earth. And then once it gets close to Earth, you can see at the top of the spacecraft here, this conical section, that is the heat shield of the Earth entry vehicle. So once it gets close to Earth, it will push this off, and that will go and hit the Earth's atmosphere and slow down going through the Earth's atmosphere. And it will land in the desert of Utah, in the Utah test range. And then we'll be able to go collect that box full of rocks that are the samples returned from Earth, and we will be able to bring them into a facility here on Earth to be able to use all of the scientific instrumentation that we have available to us here to be able to really answer some of those fundamental questions. And this seems like this gigantic arc of exploration, thinking back to the Spirit and Opportunity rovers and their search for water, Curiosity and its search for habitability, and Perseverance in its search for signs of ancient life. And it's over decades. These samples were returned to Earth, hopefully in 2031. And that is a gigantic undertaking. But I think that it is answering one of the most fundamental questions to humanity of, is life unique to Earth? And it's such an extraordinary claim to say that life is not unique to Earth, but life can evolve anywhere that these basic ingredients for life exist. But that's why we're going through this gigantic effort to provide that extraordinary evidence to be able to match that extraordinary claim. And all of these things are challenging, and some have worked and some have not worked. But kind of our motto at JPL is to dare mighty things. And I know that Ashwin and I are both extremely proud to be part of this endeavor. And we thank all of you for coming here and listening to us be able to tell this story here tonight. So that's all I had. Thank you guys very much. And I think we've got some time for questions if people want to be able to ask some questions.
Okay, well, I'll go ahead and I've been monitoring the questions as they've come in before. Before I start, I'd like to, on behalf of the, I think 114 people who listened to your two presentations, shows how much interest there is in Mars, right? So I'd like to thank you both for a wonderful presentation. I found it fascinating. Before I start the questions, I would like to introduce someone that is on the call. His name's Terry Martin, who used to work at JPL, and he's on the Science Advisory Board at ScienceWorks, who's one of the sponsors. I know Terry knows Ashwin, and I'm sure he would like me to say hi to Ashwin. So it's pretty cool that the Medford area attracts all these people. So I have a lot of questions to ask, and so let's get started. So I suppose one of the first questions we got asked, I think Matt approached this a little bit at the end. It says, why are scientists so obsessed with finding life beyond Earth? Why don't we simply go to Mars and make it habitable? And why are we so obsessed about, well, why did life exist in the past? So Matt, why don't you start?
I mean, I'll give you kind of an unscientific answer, and I'll let Ashwin kind of answer from the scientific perspective. But I mean, for me, it's this very basic question, right? Are we alone? And I think that has been a question that humanity has asked for all time, right? Is life unique to Earth, or is life able? Someone explained it to me one time that was really interesting, where we know that the laws of physics apply anywhere in the universe. The laws of chemistry do. The laws of evolution apply as well. If you get all these ingredients together, will life evolve? And I think answering that question is one of the prime questions that humans have had for a long time.
Yeah, I feel the same way. Matt answered it in a great way. I guess I'll expand on that and say, like, if we were to find that life exists on Mars, that life took hold on Mars because it was just as habitable as Earth was 3 billion years ago, or if it didn't take hold, that would tell us something fundamental about how likely it is that life exists on the billions and billions, as Carl Sagan would say, of planets around other stars throughout the universe. We have no information about how likely life is. How unique are we on Earth to have evolved life? Is it super common throughout the universe, or is it not? Even knowing that life exists one other place would give us a lot of extra data to understand that question.
Well, and another question was, you've been looking for past life, but do you think life still exists today on Mars, or we just don't know?
As I mentioned briefly in my presentation, the conditions were just so much better in the past when Mars had these flowing rivers and lakes and maybe even an ocean. Today, it's nearly impossible to think of life at the surface of Mars. It's possible it could be underground, and maybe underground it survived even from 3 billion years ago. But I personally think it was a lot more likely in the past, and maybe it's no longer there. Who knows?
And there's quite a number of questions where people really wanted to dig into detail about the kind of molecules and that you're finding. In other words, you're looking for organic materials. You're analyzing rocks and that. People wanted to try and understand a little bit more detail. What kind of molecules and are you finding, with curiosity, and then going over to Matt with perseverance. What are you looking for there in terms of actual the kinds of molecules you're looking for?
Well, I can start. I mean, Matt made a very important point, which is to really understand whether life existed, or even understand what organic molecules are present. You've got to bring the samples back to Earth, where we can use all, the kind of laboratory equipment that fills up an entire university wing. We can't put that all on a rover. But with Curiosity, we can detect carbon-based molecules that are up to kind of a certain size, and then we can't detect bigger ones than that. You know, Mars, because the organic molecules formed 3 billion years ago, a lot of them are quite degraded, we think. So we actually are only finding quite small ones. You know, methane is an example of a hydrocarbon that just has 1 carbon atom and 3 hydrogen atoms. And then you can just add a few more carbons and hydrogens, and that's kind of the size of the things we're finding. We're finding molecules with, you know, 2 carbon atoms, 4 carbon atoms, 10 carbon atoms. I think 11 is our record. So a hydrocarbon with 10 carbon atoms and a bunch of other stuff connected to it, which is, you know, big by our standards. But if you look at what's in your body and in your cells, you can have gigantic organic molecules. So we're not finding the kinds of things that are, you know, like inside of our cells, inside of the machinery of life, but we're finding maybe fragments that either could be built into those or maybe are remnants of those.
So Matt, does Perseverance have any more sophisticated tools in terms of looking for more complex molecules?
I'm gonna let the geochemist Ashwin over here answer that. I don't think that there's any fundamental difference in our ability to detect things. I really think it's about our ability to map it. Is that correct, Ashwin?
Yeah, no, you're right. You know, in fact, Curiosity with the laboratories probably has more capability to detect organic molecules than Perseverance. But what Perseverance it does differently and better than Curiosity is, one, it gets those samples ready to come back to Earth, which is huge. And two, as Matt mentioned when he was talking about the big instruments on the end of Perseverance's arm, you can actually look at a rock at kind of a microscopic level of detail and see how the carbon is arranged in the rock itself. And that itself is a clue whether life made that arrangement or not. All we can do with Curiosity is drill the rock. It just comes out in a big pile of stuff, and then we can see if there's any carbon in it. We can't map the detailed structure of the rock to see if there's kind of a fingerprint of life.
So Matt, here's the question for you. You talked about the helicopter. There's virtually no atmosphere on Mars. So how can a helicopter work in that environment?
Yeah, so there's a very thin atmosphere on Mars, and it's about 100 times less dense. So that's why we have to have those really big rotor blades, and why they have to spin so fast, and why we can only carry a little tiny, you know, basically the payload is a GoPro camera that will fly around and capture images. And that's really the challenge of flying on this other body, right? If you were on Venus and you had this really dense atmosphere, it'd be great. You could fly with these really tiny little blades. But the challenge is making something that will fly there. And we've done some tests here in chambers on Earth where we can pump them down to have the same density as the Martian atmosphere and watch it fly around. So we know that it can work. It's just getting it to work with all the variables of dust and wind, and has to do it autonomously because of that time delay. So bringing all those things together are the challenges to really making that Ingenuity helicopter work on Mars.
So now the rover, this is another question. So the rovers, you pre-programmed to perform certain actions. With the helicopter, presumably, you're going to have to do the same thing, right? You're going to have to you can't control it dynamically. You're going to have to pre-program it.
Exactly. And it has to make its own decisions. So to me, that's what makes the robots so amazing, right? They have this autonomy on board where the helicopter will take off and it will have to keep itself stable, and it will have to fly its own trajectory. And then it will have to look for a safe landing spot, right? It will have to examine and say, is this safe? Are there rocks there? Are there not rocks there? And it will have to find its own landing zone. And it has to do that all on its own. It's an amazing piece of engineering.
So there were some other questions about, you've both been talking about drills. So there's a drill on both rovers. Now, the other mission to Mars was InSight. It had a drill which wasn't capable. They've given up. NASA's given up trying to drill into the surface. So how come both rovers can drill into the surface, but InSight can't?
That's a great question. And the InSight mole, it's not quite a drill. It's a very unique design that uses a hammer. So it's an internal hammer, and it's able to kind of drill itself into the ground. And the main difference is We have 900 kilograms of rover pushing on a drill, where InSight has to do it all on its own. And the InSight drill, the mole was able to go a little bit, but then it hit something unexpected in the subsurface. And we anticipated that it to be kind of an unconsolidated material that didn't have a lot of kind of hard material in it. And I don't know what it found in that subsurface, but after a while, it was no longer able to make progress.
So going back to the drones, another question just came, a follow-up question. So how long can the drone fly for? I mean, how long will this experiment with the drone last? And when it goes out and flies, how long can it last for? And really, what powers it, I suppose, is the other question.
Yeah, that's a great question. So it's an engineering experiment, and we will take baby steps, and it will happen kind of early in the mission. We don't know how long the drone will last. It's all kind of made with commercial electronic parts. It wasn't made with the same reliability as the rest of the rover. So early in the first couple of months of the mission, it will try and just hover off the ground and then go back down. And then it will go up and it will hover a couple of meters off the ground, and then it will come back down. And the next flight, it will hover a few meters and then translate a few meters and then go back down on the ground. And I think the longest that it can fly is probably a couple of 100 meters. I don't know the exact answer, but it is powered by a small solar panel on top of the helicopter. So it charges over many days, and then the battery on board enables it to make those short flights. But we're not expecting it to go explore, large geological regions. It's really just an engineering experiment to see if we can make helicopters work for that kind of broader exploration in the future.
Mm-hmm. Going back to Curiosity as a question for Ashwin. So, the Curiosity's been on Mars for about 3,000 sols now. So, and as you said, a sol is slightly longer than an Earth day. And it's driven about 15 miles, as you pointed out. So one problem that Curiosity ran into was some damage to its sort of wheels. And the question is, well, Curiosity mission has been extended indefinitely. I mean, how much life does Curiosity have left in it?
So Curiosity, we don't know what will eventually be the end of any of these missions. We do know that Curiosity has something that is running out. We do have a kind of a clock, which is our power source. So Curiosity is powered by what's called a radioisotope thermoelectric generator, which means we actually have, and same with Perseverance actually, they both have plutonium in the back of the rover that gives off heat, and that heat is turned into electricity that powers things like driving and keeps the rover warm as well. And that's one of the things that will limit the productivity of Curiosity as we get into the next 8 years. So we're not about to stop anytime soon, but over the next 3, 4, 5 years, we'll have less and less energy to work with. So we might have to take more days off, give the rover more days off to recharge its batteries. The wheels, we were worried at about Sol 400 or so, and Matt remembers as well too, that might be what limits the productivity of the mission. But actually, through a lot of work by, Matt and I are just one example of a lot of ways that scientists and engineers work together at JPL to solve problems. And one of the things that we did when we discovered the wheel issue is scientists mapped out the geology of Mars that was causing the problems. The engineers went and figured out if there's anything we could do to drive in a better way, or how maybe the mechanics of the wheels themselves were contributing to the damage, and could we change anything with the software? All those things came together and really have solved the issue of the wheels for us. We're no longer worried that the wheels are going to be a limiting factor.
So are this question for Matt. So are the wheels on Perseverance the same as on Curiosity, or were they improved or changed as a result of Perseverance?
We spent a lot of time making sure that we weren't going to have that same problem again. And we designed a much thicker wheel. The reason that we got the wheels to where they were for Curiosity was, we can only land so much mass on the surface of Mars. So every kilogram we spend on a wheel is a kilogram we can't spend on a science instrument. And we want to do as much science as we can. So there's a ton of pressure for the engineering staff to reduce the mass of all of their components as much as possible. And we did all sorts of great testing to show that, you know, the sharpest rock, you could put the rover on the sharpest rock on Earth and it wouldn't cause any problems. But what we didn't account for were these forces that the wheels make against each other as they drive through this terrain that has extremely sharp kind of ventified rocks that are all embedded in the terrain. The wheels are fighting each other and they're able to generate, you know, 2 to 3 times as much force as a wheel just sitting on a rock would generate. And that goes into that testing. You know, we spent a ton of time testing, but we didn't actually test in the right conditions. And that was a lesson that we learned. And one of the things that I think is so cool about these missions is every mission has stuff like that happens, right? The mole doesn't work on InSight as we expected. The wheels on Curiosity are falling apart earlier than expected. And we will have similar challenges with Perseverance. We don't know what they are. We hope we've solved all the problems from our previous missions, but new problems await. And that's just part of exploration. And it is part of the mentality and culture of JPL that when we encounter those problems, we all just roll up our sleeves and we figure out a solution, right? There's no finger pointing of it was your fault or how did you let this happen? It's let's figure out how to do some good science with these amazing assets that we have. And I'm really proud of being part of a team that is able to do that, because that allows us to try things where we might fail, but we also might be wildly successful.
So going back to what Ashwin was talking about when we were talking about powering the rovers. So one person was disconfirming. So there is effectively a thermonuclear reactor on the back of both rovers. Is that right?
Not quite a reactor, just, you know, a ceramic block that contains plutonium in it. And that plutonium is naturally radioactive and gives off heat. So it's actually quite simple. It just gives off heat and we turn that heat into electricity. We'd love a reactor, but that would be much more complex than what we have.
And
Hey, Colin, do you mind if I ask a question of Ashwin?
no, not at all.
Hey, Ashwin, I was following Curiosity, you know, a few years back, and I found out that, or I've learned that you guys found a methane cycle that was seasonal. I was just wondering what is your team and what do you think, you know, is creating that methane cycle that you found in the atmosphere?
Yeah, it's a fun mystery that we've spent a number of years now trying to solve. So, you know, there was a question earlier about whether we think there's life today on Mars versus in the past. And one of the only real clues, I guess, or hints that there might be something going on today is the fact that there's methane in Mars' atmosphere when there really shouldn't be any. Methane gets destroyed pretty quickly in Mars' atmosphere. Yet, even before Curiosity arrived, the satellites we have at Mars started to detect big clouds of methane occasionally. And that could be, for example, a result of microbes that live underground that are giving off the methane, and it's going into the atmosphere, being produced. So before Curiosity arrived, we were very interested in detecting the methane ourselves. We actually made sure we had a sensor capable of doing that. And we landed, and at first we didn't see any methane, but then we started to detect these very low levels. And not only did we detect levels of methane, but we detected the fact that it kind of seasonally varied. It was higher in some parts of the year and lower in others. And of course, we also did a lot of work to figure out what could be causing it. And, you know, to attribute something to life is a big deal for all the reasons that Matt and I both discussed. So, you know, when we're talking about something that could be evidence of life, we want to do our work to make sure that there's nothing else that could be causing it. And we actually have found, you know, there are natural reactions that go on with rocks underground, especially if there's liquid water underground, which there might be today on Mars. Just the interaction of water with some types of rock can give off methane gas. And that could explain what we're seeing. So, you know, the answer to your question is we have this very intriguing methane variation. Methane is being produced by something, otherwise it wouldn't be there if it wasn't actively being produced. It could be life, but, you know, the more likely answer is that it's some kind of natural reaction underground.
Thanks.
Yeah, one person asked actually, is it possible that life on Earth could have been seeded from Mars?
I mean, just briefly, one thing that's fascinating about Mars is that Mars was so habitable. You know, the delta that is in the crater that Perseverance is going to, and Mount Sharp in Gale Crater, both formed, 3.5 billion years ago. Where on Earth at that time, life wasn't doing too well. So Mars was friendlier to life earlier than Earth, and so who knows? Mars may have flourished life, and then that came to Earth, but we don't know.
Because we do see meteorites, right, on Earth that came from Mars.
True.
Yeah. A question for Matt about the return. So people were asking about the date of the return. If I remember right, you said 2031, right?
Yeah, our goal is to launch our mission in 2026. We're taking a longer route to get there, so we will land in 2028, collect those samples, and then it takes a while for that solar electric propulsion to get the Earth return orbiter back to Earth, and we're hoping to have those samples on the ground in Utah in 2031.
So, I mean, given if we look at Perseverance, it was launched in July, it's arriving in February, which is this month. And so presumably that's just because of the position of Mars plus the actual rockets you're using, that it's taken like 2 years to get there and 3 years to get back, right?
Yeah, it's actually very intentional. So one of the things that is related to this is that our missions on the sample return are solar powered missions. They don't have this radioisotope thermoelectric generator, this plutonium on it. So we really need to land in the summertime, and we don't want to land in the winter because it's dust storm season. And if we have a global dust storm on Mars, it would kill our solar powered missions. So because of the trajectories of the planets and when they're closely aligned in 2026, if we want to land in the springtime, we have to take this longer route. So it will take about 1.5 years for our mission to get there, where Curiosity took about 9 months and Perseverance took about 7 months, because they can take a more direct route and they are able to land in different seasons because they're not solar powered missions.
Going back to Curiosity and Perseverance, I asked a question, what kind of lasers do they have on the two rovers?
Awesome lasers.
Yeah. I used to have that spec memorized. I don't anymore. I'm sorry. But it's like a 1 micron wavelength. So just beyond red laser. I can't remember the kind of laser. Just powerful enough to put a little 0.5 millimeter size crater into a rock.
Yeah, I think people have visions of the rovers driving around blowing up the place, right?
Right.
So there were a couple of questions from some youngsters on it. Well, are you going to bring the rovers back again? And I think the answer is to that, no. But the question is, well, if we take the helicopters and the 2 rovers and that, what's going to happen to them in the future when you're no longer using them? They just, like everything else, become artifacts, right?
Matt Damon's going to go hang out with them on Mars. But yeah, we don't bring our missions home. They will be there forever on Mars, and we can go see where there's a lot of past missions. We can see from our orbiters, the Viking the landers that landed, and we can see the Spirit and Opportunity rovers that are there now. So we are littering Mars a little bit with our spacecraft, but my hope is that someday we'll go get them and bring them back and put them in the Smithsonian, but it'll probably be a long time before we go do that.
Yeah, most probably not in my lifetime.
We're looking for volunteers if there's anybody out there that wants to volunteer.
Well, on that subject, there have been a number of questions, and maybe it might be as we head towards, we're running out of time here, but there were questions like, well, what motivated you to take the careers you did and go to JPL? Like, for example, Robert suggested I ask the questions because he knows I'm into robots and robotics, and he thought I'd like to chat to Matt. And people were asking questions like, well, will you remember the first robotics league and things like that? So how do I get involved in doing this kind of stuff? What motivated you? So perhaps you can, why don't you go first, Matt? What motivated you to do what you did and go to JPL? And specifically focus perhaps more on robotics?
Yeah, so my career I think is different than a lot of others, where my focus is robotics, right? And the robots that I work on happen to be driving around on Mars, but it's the same technology that would go into your Roomba that vacuums your floor, or self-driving cars that Google and Uber are developing. They're really very similar technologies, and to me, that's the thing that's amazing. When we can make a machine and that machine can make a decision, that's why I do what I do. And FIRST Robotics didn't exist when I was in school, but I have since been a mentor and a coach. So I coached a team in the first Lego League, and I've been involved with the FIRST Robotics team at St. Mary's there in Medford quite a bit. And the thing that I would say is that FIRST Robotics program is very much like engineering and robotics in industry, where you're given a very challenging problem. You have to work as a team with people with different disciplines, right? Some people are writing software, some people are building hardware, and you're coming together to build this thing that's way more complicated than any one person could do. I think we had 3,000 people that worked on the Curiosity rover, and it's just this amazing collaboration. So that's why I love what I do and why I came to JPL. Ashwin?
Mm-hmm. For me, it was the perfect mix of two things that I love. One is understanding how the natural world works. So I've always liked science, but then I really in college figured out I really love understanding how science works in the natural world, understanding geology or understanding atmospheric science and meteorology. And then the other thing that I've always loved since I was a kid was the idea of exploring. And I remember seeing pictures particularly of landers on Venus and Mars. So, the flybys of Jupiter were cool, but it was, you're millions of miles away and you're flying by. But when you have a robot on Mars and you're taking pictures from eye level, just like you're standing on that surface, that fascinated me. So what better thing to do than understand how the natural world works while exploring another planet?
Yeah, I think great answers. And going back to First Lego League, I've also refereed and added a judge on First Lego League, and I really would encourage any kids listening to go and join those programs, which is more difficult at the moment because we're in this sort of virtual environment. And in fact, there were quite a few questions about JPL. I was very fortunate, JPL before we had COVID ran tours. You could get tickets for that. And I went on a tour just before the Perseverance rover was finished, and I saw it finally being put together, and that was an incredible experience for me. One thing I do notice that JPL actually has a virtual tour at the moment, so you can't physically go there at the moment, but you can go on the NASA website and go on a virtual tour. But when things improve again, I really encourage anybody listening to go on that tour. It's a fascinating place. I really envy you guys working there. The other thing I was going to point out before I hand back to Robert, because we've run out of time, is I gather there's something like 750,000 photographs of what the rovers have taken, and Ashwin's been showing a lot of them. I believe those are all available on the NASA site, right, Ashwin?
Correct. You can go to, just search for Curiosity JPL and Google will take you there. And same with Perseverance. There's actually a Mars part of the JPL website that'll get you to both missions. And every image we've taken and lots of blog entries and things like that you can find.
Very good. Well, I'm going to hand back to Robert. I'd like to thank both of you for the presentation, answering our questions. Good luck on February the 18th. I'm going to have my fingers crossed. We hope to do a session like this the night before, which happens to be our astronomy group meeting. And so we're going to really sort of sit with bated breath and keeping our fingers crossed for you both. So good luck to both of you, and thanks. And I'll hand back to Robert.
Okay, thank you, Colin. Gentlemen, thank you so much. That was a lot to learn. Can't believe that you both decided to join us tonight. Thank you so much, and can't wait to hear more. We're going to follow you on February 18th, and really got our fingers crossed, just like Colin said.
Yeah,
Thank
me
you to
too.
Yeah, I bet. And last thing I want to say too is I've used the landing of Curiosity there the summer of 2012 in the planetarium programs I do. And it was just one of the most exciting things that we've ever seen. And I showed it for years. The kids never got tired of it. So thanks for making these moments for educators and motivating people and inspiring kids. So thank you
Thanks for
very
having
much.
us.
Yeah.
Thank you.
Bravo. Thank you.
Mhm.
Everybody take care. Thanks a lot.
Thank you, everybody. Good night.
Good night.